Okay, earthquakes are violent shaking of the earth. It's a way that the earth is going to release energy, built up energy, found in certain locations. Now, where are those locations? Okay, earthquakes basically occur along what are called plate boundaries. You have to think about the Earth's crust, or the lithosphere, is broken up into different sections. Those different sections move, and they're going to crash together, they're going to pull apart, or they'll slide side by side. Wherever those plate boundaries are going to interact, that's where you're going to get a release of energy. Usually along those plate boundaries, okay, where the earthquakes occur, those are what we call fault lines. Fault lines are cracks in the rock where rock moves, and whenever the rock moves, that's where the earthquake is going to occur and energy is going to be emitted. So here's a map that shows you the major plates on the planet, and with each plate you're going to get different interaction, whether crashing together, pulling apart, or sliding side by side. Now your world earthquakes are going to occur along those plate boundaries, and usually along those plate boundaries you'll get what are called fault lines. Now there's three basic types of faults. You have normal, reverse, and strike slip. Strike slip is probably going to be the most important one because that is the San Andreas Fault that's located in our own country in California. So San Andreas Fault, out of those three types of faults, San Andreas Fault is a strike slip fault that's found out in California. So the prefix size means earthquake. So you get seismologists, those are people that study earthquakes. Seismographs are the machine that records earthquakes. A seismogram is the recording or the printout of how violent the earthquake was. You get a seismic station, which is the location where seismographs are housed. And you also get seismic waves, which include your P waves and your S waves. So you have a couple different parts of the earthquake. The focus is actually spot inside the earth where the earthquake actually occurs along the fault line. It's where the energy, the P waves and the S waves, are actually emitted. Directly above that, at the surface, is the epicenter. And then you also get your seismic waves, the P waves and the S waves. So there's a picture of the focus. You notice that occurs right along the fault line. Directly above the focus, that's your epicenter. So you need to know your characteristics of P waves. They are called compressional waves. They are also known as primary waves. They are also first to a seismic station. They are faster than an S wave. They travel in a push-pull motion, and they can pass through solids, liquids, and gases. They're fast like a Porsche. So you notice that all your characteristics start with the letter P. I actually got that idea from Mr. Sammartano. So there's your P wave, travels like a slinky, and you see the compression as it's going to travel from the person's hand to the wall. The S waves, they're shear waves. Secondary, slower. Second, travel through solids only. They travel in an S-like pattern. And they're slow like a Saturn. So think about the two cars, the Porsche versus the Saturn. And there's your S pattern with the rope. Again, you can see how it's going to travel in an S-like pattern from the person's hand to the wall again. So once you identify your characteristics of P waves and S waves, you can get what are called seismograms. And seismograms are the zigzag pattern that represent the shaking of the ground. Now notice, the P wave arrival and S wave arrival at station A are a little bit farther apart than the P wave arrival and S wave arrival at station B. Well, that tells you that the station A is farther from the earthquake, station B is closer. The closer your arrival times are, the closer you are to the epicenter. Now, epicenter locations can be very important to us. The magic number here is 3. Whenever you have to draw your epicenter circles, you need a minimum of 3 seismic stations to figure out exactly where the earthquake occurs. One station just gives you distance. 2 stations will give you 2 possible locations where the earthquake occurs. 3 stations will give you the exact location because you want to look where all 3 circles intersect. Let me demonstrate. Map of North America. You have station A, B, and C. A is 1,000 miles away from the epicenter. Not sure exactly where it is, so what's going to happen is a circle will be drawn around letter A. The earthquake can occur anywhere, an infinite number of points around A along that circle. So 1 station gives you just distance, not direction. 2 seismic stations help you narrow it down to 2 possible locations. B is 1,500 miles away from the epicenter. You draw a circle around B, you notice now your 2 circles intersect at 2 possible points. You need a 3rd seismic station, and in this case, C is 2,000 miles away. You draw a circle around C with a 2,000 mile radius. And what's going to happen is you will notice that the 3 circles will intersect right in the center of the country, right where the black arrow is. That is your epicenter. Now we have 2 scales that we go by. We go with the modified Mercalli scale, which measures the amount of damage created. It goes from a 1 to 12. You can see this is a map of the 1964 earthquake in Alaska. You see right in the center of that map, okay, you see a little star. That star just to the eastern part of Anchorage is where the 1964 epicenter was found. You notice that the Roman numerals, okay, go up to as much as 10 on the Mercalli scale. And as you get farther and farther away, those Roman numerals get smaller and smaller. So you go from a 10 down to a 7, down to a 6, down to a 5, down to a 4, and a 3, the more north you go. So you'll notice that the Mercalli scale, the greatest damage, is right at the epicenter. The one scale that we're a little bit more familiar with is the Richter scale, and that goes from 1 to 10. The example I have here only goes up to 9, and they give you the equivalent of dynamite, how much dynamite you would need to trigger the amount of energy given off by a specific earthquake. This is the scale that we're much more familiar with. The bigger the number on the Richter scale, the stronger the earthquake was. So that leads us into what we call shadow zones. Okay, shadow zones are areas where you do not receive P waves, S waves, or both P waves and S waves. So we know that P waves can travel through solids, liquids, and gases. So why do we get a P wave shadow zone? It's caused by refraction. Because of our different layers in the Earth have different densities, our P waves are going to change direction as they go from one layer to the next. And as they change direction, they're going to miss their targeted point as they travel throughout the Earth. The deeper the layer, the higher the density, the more the P wave is going to refract. So you can see in this diagram, there is a zone on the bottom right-hand side of this Earth and the bottom left-hand side of this Earth that do not receive P waves. Not because P waves can't go through different layers, it's because they refract, entering the outer core and exiting the outer core. They'll bend. So you get 2 little zones called the P wave shadow zone. The S wave shadow zone is a little bit more prominent, and this is all caused by that liquid outer core absorbing our S waves. So we know that S waves cannot pass through liquids. That outer core absorbs it, so you get a very, very big zone exactly opposite the epicenter. And you can see the massive zone that does not receive S waves very simply because of the liquid outer core. Now I'm going to take my P wave shadow zone and put it right on top of my S wave shadow zone, and you can see where P waves and S waves are received, where only P waves are received, and where no waves are received. So you need to know your difference between the P wave shadow zone and the S wave shadow zone.